Good morning, everyone. Thank you very much for the kind introduction from Professor Koichiro Ishibashi. It's my honor to present my talk entitled UAV-Assisted Communication for Performance Improvement in Cellular Networks. And this work is done in our group of Advanced Wireless Communication in Quy Don Technical University in Vietnam. And this is the outline of my presentations. First, I would like to give a brief introduction about our work, and then I would like to give a brief introduction about UAV-assisted communication system, and then I will talk about the application of UAV-assisted communication in science network for beyond 5th generation or 6th generation. And finally, I would like to conclude and give some future directions. So first I would like to introduce about the UAV applications. UAVs is briefed for unmanned aerial vehicle, as you all know. It also known as drone, which have found its application in various scenarios, such as aerial photography, search and rescue operations, precision agriculture, express shipping and delivery, remote inspection and safety surveillance, unmanned cargo and transport, and also law enforcement and border control surveillance. So as you can see in the slide, these are two examples of using UAV for delivery and also for search and rescue operations. And what is the UAV-assisted communications? UAV-assisted communication is a kind of communication, a UAV-mounted transceiver to assist wireless system. To the right of the slide here, we can see an example of small UAV-mounted transceiver, which is produced by microcontrollers. And UAV-aided or UAV-assisted system can provide efficient, cost, flexible, and reliable communication with high mobility, ubiquitous coverage, easy programmability, fast deployment to meet on-demand communications for both military and civilian applications. Yes, I would like to give you some example of UAV-assisted communications. This slide shows two examples of using UAV-mounted relay, which act aerial relay station to provide connectivity for non-life size or hard-to-reach area, such as for the tactical communication for military operations and for providing connection using cellular networks to the flooded or earthquake area. This is another example of using UAV for communications. In this slide, the UAV is mounted, a base station, small base station is mounted on UAV, and it can operate as an aerial base station. A hotspot to provide connectivity among ground users, for example, for search and rescue operations. Here is another example of using UAV for communications. In this slide, UAV mounted wireless camera or UAV mounted transceiver can operate as an aerial user to provide transmission for real-time video or collect sensory data from a wide coverage area. So we can, from the three examples, we can see that UAV-mounted transceiver can work as either aerial relay stations or area UAV-assisted communication systems. Here, I would like to draw you to two examples of UAV-assisted communication, which are already deployed in Japan. The figure to the left shows an example of using UAV as a flying base station for using that disaster, provided by SoftBank entity, KDDI, and other company in Japan. Another example is using UAV also for disaster recovery or locating person trapped under debris, which was demonstrated by SoftBank in 2020. And with the inherent properties of UAV, such as flexibility, mobility, and adaptive UAV-assisted communication is now being considered a promising solution for the beyond fifth generation and also sixth generation of cellular networks. And together with the Internet of Things IoT in the context of Industry 4.0, recent researchers have also foreseen the birth of Internet of UAVs, or also known as the Internet of Drones, in the beyond fifth generation or sixth generation cellular networks. UAV has also motivated the concept UAV to the X communication, and X here means everything. Here is an example of using UAV-assisted communication for beyond fifth generation or sixth generation cellular network. In this scenario, UAV can help to provide extremely reliable and low latency communication service. Here, so we can see example of transmitting live video to, for example, broadcast to the TV broadcaster by the cellular network. UAV can also help to provide the ultra-massive mercantile communications, such as in this figure to the right, to collect sensory data from a wide coverage farm to the centers. UAV can also help to provide a further enhanced mobile broadband service in the fifth generation or sixth generation networks by providing better connections for the mobile users. In our group, we recently have started doing research for the UAV-assisted communication system, and I would like to introduce you to some of our initial results in UAV-assisted normal MIMO wireless. So in our research, we consider a UAV-assisted non-orthogonal multiple access, multiple input, multiple output system, which is abbreviated as normal MIMO, for performance improvement in cellular networks. And we have carried out a theoretical analysis for this UAV-assisted system. This is in this slide we show the scenario of our research, and here in this network we use an UAV-mounted base station to serve as an aerial base station to provide large coverage for densely urban area, such as in a crowded city with high buildings. The area base station uses MIMO for high rate transmissions, and to support multiple user access network, we use NOMA, that is a non-orthogonal multiple access, already being used in the fifth generation of cellular network at the multiple access scheme, because it can mitigate the co-channel interference and also achieve high spectrum efficiencies. And here we consider the case of two connection between the source user S2 to S1 to the destination user D1, and also another connection from the source user S2 to the destination user D2 here. And we assume that the UAV flies with the speed V smaller than Vmax, capital Vmax, at a fixed high H and along a linear trajectory while serving ground users. And the channels between the source nodes and the destination node here, and from source node to the aerial base station, and the channel from aerial base station to the destinations, depending on the position of the UAV, it can be life size or non-life size, and are affected by the Doppler effect due to the UAV mobility, which causes both large-scale and small-scale feeding. So in order to see how UV-assisted communication can improve the performance system, we try to find the probability of obtaining the live size for the connection from the ground user to the UAV and from UAV to the ground user. So here's the equation that we can achieve to calculate the probability of obtaining live size and non-live size, so that we can do some analysis. And here we can calculate the probability of live size for 3 different environments, which mean suburban, urban, and also densely urban. And this slide shows the probability for obtaining live size and non-live size for 3 different areas, meaning dense, urban, and suburban. So we can see in this figure that we can have a high probability of obtaining a live size in the suburban area than in the densely urban. And also the probability depends very much on the elevation angle between the UAV and the ground users. And we carry out outage probability analysis for this system. And the obtained figure to the left here is the impact of UAV speed on the outage performance. And here we analyzed for 4 cases of UAV speed, that is 0, 10, and 30 meters per second, and we analyzed for 2 users, user 1 and user 2. And from this figure, we can see that the outage probability increased due to Doppler effect as we UAV velocity. However, the outage performance becomes saturated at the area of about 30 dB for SNR here. This is due to the residential channel interference in NOMA scheme, because we use our domain NOMA scheme. So when we increase average SNR, then the residential channel interference exists more, so it causes the outage probability to become saturated in high SNR regions. And this is the figure to the right here, show the impact of UAV height on the outage performance. And we also conducted for suburban, urban, and densely urban area. And from this outage performance figure, we can see that the outage probability decreased for the high less than 25 meters, but increased for higher altitude. This is because when we increase the higher UAV, we can obtain more probability of live size link between UAV and ground user. So the outage probability reduced for the high from 10 to less than 25 meters. But when we increase further the UV high beyond 25 meters, the distance of the link between the UAV and ground user increase, so the outage probability also increase. In this slide, we show the impact of imperfect successive interference cancellation due to NOMA scheme on the outage probability. Horizontal lines here show the imperfect successive interference cancellation coefficients. So we can see that the imperfect SIC has a big impact on both 2 users, user 1 and user 2. However, the outage probability performance of the user 2 is worse than that of the user 1, because user 2 is detected after user 1 by normal scheme, so it is influenced more due to the imperfect success in interference cancellation, or is affected by more residual interference. The figure to the right here shows the performance comparison between the case of using NOMA and OMA. OMA is orthogonal multiple access, which is the multiple access using either time division or frequency division multiple access. And here we can see in the figure that because in the OMA multiple schemes there is no interference, so the outage probability is not affected by the saturation here. As we increase SNR, the more SNR is, the better outage probability performance OMA can get. But for NOMA, due to the residual interference, it will become saturated. In UAV assisted system, the UAV lifetime depends on the battery. So if we want to serve the network longer, we need more energies for the area base stations. So we conducted another research by considering using the energy harvesting from TV or radio tower, so that the area base station can collect the energy via the energy harvesting link to support the communication in the network and carry out similar analysis with the previous work. And here we assume that we use time switchings with the switching factor alpha smaller than 1, and in a period of time, part of the alpha period of time is used for energy harvesting, and the remaining period of time used for signal processing. And the ABS use the energy harvesting period to harvest the energy from the broadcast signals from either TV or radio tower, radio transmitter. And we assume that the harvested energy is used to charge the UAV battery. And then use a scenario similar to the previous work that we already introduced. So in here, the figure to the left here show the impact of the switching, the time switching ratio between energy harvesting and signal processing on the outage probability performance. And here we show that our radio transmitter also use MIMO antenna to carry out our analysis. So here we assume that the broadcaster transmitter has NT antenna, and the number of NT antenna equals from 1 to 3 here. We can see that by using more antennas at the transmitter while keeping fixed transmitter power helps to reduce outage probability and also switching ratio. We can see that if we increase the number of antenna, the outage performance reduce here. And also by using more antenna, the time switching, the required times for energy harvesting is also reduced here. And the figure to the right here shows the outage performance by using a power allocation scheme. And we investigate the case of using power allocation to find the optimal outage probability. And in this, here we can see that by using a probably power allocations scheme, we can achieve an optimal outage probability. For example, for the case here, we can achieve by using the power allocation coefficient equal to 0.65, we can achieve the outage probability about 10 to the minus 4. So just some conclusion and future outlooks. UAV assisted communication is a promising solution for providing cost-efficient and reliable communication in cellular networks. It is possible to harvest energy to prolong the UAV lifetime if multiple antennas are used at the TV or radio transmitter. And in the future, we intend to fabricate an area of base stations for implementing the UAV assisted system using software-defined radio. And in fact, in our group, we also done some initial on fabricating the UAV and also the compact base station for 3G and 4G cellular network. And we intend to use a software-defined radio for the ADS, which is area base stations. And that is our outlook. Thank you very much for that.